Hello, and welcome to Corvid Coder. This is the stream where I code things, and you watch and get to learn. So, we'll be starting up a new project in parallel with my other ones. But this is a project that I've been wanting to do for a very long time. I figured now is the right time to do it. I've been wanting to make a Gameboy emulator. So, let me point you to some good resources for Game Boy stuff real quick, and then we'll go talk about what a Game Boy is and look at it. Very admittingly, these first few videos will probably be very, very boring. It'll be me reading through documentation and then implementing a CPU, which is a very non-visual thing. So the GBDev Game Boy awesome list on GitHub is really good. So yeah, it's this one. So this has a ton of resources, communities, you can join like the Discord server and stuff like that. There's all the documentation you can need, including the official Game Boy programming hardware manual. I'm not positive this link is even legal, so I'm not going to show it on stream. Oh wait, this is the official one. Yeah, by Nintendo. I'm pretty sure that this shouldn't be shown on stream. However, there is another one, this one here. So the Game Boy CP manual is a really good starting point, and this is made by an individual. Or I guess individuals, many individuals, and this is what we're going to be using on stream. If there's anything, there are literally a couple discrepancies in here that are not right, but for those, I'll look at the official manual off screen that I don't own. I don't have it, so I can't really look at it, right? But I'll be referring to other sources when this doesn't work for us. So, I think with that, I wanted to make sure everyone's aware of what the Game Boy is. I understand not everyone's the same age as me. So, the time when they might have been playing Game Boy didn't quite line up. I love these YouTube recommended things for for someone who might be coming to YouTube for the first time. Okay, so let's just look at Game Boy. So let's watch this. This sounds like fun. So I haven't watched any of these videos yet. I don't know.
If you write anything on your computer,
and I don't want to subject anyone.
Hey guys, this is Austin, and today I'm here with a really fun one. This is an original 1989 Nintendo Game Boy. Not a smartphone. Oh no, this is the old school, the original portable handheld. If you hadn't noticed, I am a giant fan of Game Boys, and nothing gets me more excited than what's been something that's been literally sitting in the box for 27 years. First of all, this box is an incredible condition.
Oh, that is a cool box.
Official Game Boy compact video game system. In case you were looking for the unofficial Game Boy, the Game Boy system features a complete library of exclusive Nintendo game packs. We've got Super Mario Land.
Okay, so you don't need to watch all of it. I don't even know if YouTube will let me upload my video now that I'm watching YouTube videos, but so this is what the Game Boy looks like. Might be better for me to get images of it. So this is your volume. I actually don't know what this is. A serial port probably for network play. You have a power switch. Let's see if we can get other angles. I guess I should be going for images. Okay, so this is a pretty good image. So it shows the power switch on the top with the cartridge slot. So this is a cartridge that you slide in. These are going to be your games, your programs for the Game Boy. They go down maybe about this far. This is your battery compartment. These are the buttons you have. You have the 4 directional keys. You have an A and a B button and a start and select. I believe it is mono sound. I don't think it's stereo. I believe this is a headphone jack. This is volume, like I said. This is, I believe, your serial port for network play. It wasn't really used too much. It was like Tetris was the only one I used it for. and then an indication of like your battery and power. So let's look at a real Game Boy now. So here's one in the guy's hand with the screen on, which is nice, playing Tetris. So it was not backlit, so you needed a light source shining down on it in order to see it like you're reading a book. As far as I know, in all the games I played, start and select were not used in game mode other than to pause the screen, and I can't actually say that select was ever used, which is kind of amazing, considering those two buttons here. Might be a hardware limitation for people not using these in game much. But basically it was these 6 buttons that were used. So the 4 directional and the 2 AB. So there were other renditions of the Game Boy. So there were many renditions of the Game Boy, but there's the Game Boy Color. So the Game Boy Color is essentially the same hardware as the Game Boy. It runs at twice the clock speed and has a little bit more memory. And the screen can display more colors. But by and large, like the architecture of the two were almost exactly the same, which is kind of amazing in itself. We're not talking about the Game Boy Advance. We're not talking about the Game Boy DS, anything like that. So here's I believe it's the SP. Yeah. So this is the Game Boy Advance SP. We're not making one of these. We're actually not making one of these either. Game Boy Color, but I would like to emulate a Game Boy. And then once we get that going, maybe I'll look at the Game Boy Color, because it's not a very large leap from there. So these are 2 different editions of the Game Boy. This gray one is like the one that most people had. At least most people I knew. I guess I've seen a couple of these teal ones around when I was a kid. Or at least I have. Well, maybe, no, this is the one I saw. Game Boy Color teal. So later on there was the DS's. I wonder if there's just like a good Wikipedia article I can go to. What? I was worried about the DS. Wikipedia. So let's just see if they show us them all. So here's the original Game Boy. Game Boy line. Okay. So here's a cool picture. So show me the full version of this. Was it not called the Game Boy DS? It was just a Nintendo DS, wasn't it? So you have the original Game Boy. I own this one. And then we had the Game Boy Color. I also own this one. Oh wow, there was a Game Boy Light. I don't know what this one was. I'm also not familiar with this dark one. And then the Game Boy Advance SP. I had one of these. And this was like the micro. I definitely didn't own one of these. But yeah, I skipped all of these. I skipped this one, and I didn't have these two. I did have a DS actually, now that I think about it. I bought one from my brother when he stopped using it or wanted money for some reason. Okay. So the Game Boy came out in 1989. So we're emulating a system from, what is it? 19 years ago? No. 29 years? 29? I can't do math. So if it was 18, if it was 19 right now, minus 10, minus 10, 29 years ago. Yeah. So that's a long time. Oh, that was the Pocket. I vaguely remember advertisements for the Pocket. I never owned one. It was like a smaller version or something. Nah, I don't remember ever seeing one. So here's the original Game Boy. So DMG. Oh gosh, I should know what this stands for. It's something digital master game. I believe it has something to do with the screen. Let's see if I can just find out what or Bing, I guess. I don't know why it's on Bing. Dot matrix Game Boy. So yeah, it did have to do with the screen. So it's a dot matrix Game Boy. I don't know what that stands for. Master, Mega, and the Color Game Boy, the Advance Game Boy, the Advance Game Boy SP, I don't know why it's called Oxy. It's the micro. How much? Wow. It was only $100 when it came out. Wow, only $90. $60. My gosh. Oh, so this never came out in the US, the light version. Color. 80? Wow. Why does this seem so cheap? In the advance, $150 immediately. $100, so this one was cheapest. These ones were backlit too. That was the nice thing. It had this was a little light button on it, so you wouldn't need an external light source to play it. It had a backlight so you could play it in the dark. So here's the resolution of the screen, 160 by 144. Oh yeah, here. Oh, I guess there is a backlight and a frontlight version. I don't know which version I have, but I feel like it was a backlight. Who knows? So the Game Boy was able to support 4 shades of gray. So I believe that's like lightest, gray, like another gray, light to very dark olive green. So the color of the display was kind of greenish. I don't know what this one is. Oh, it's the size of a pixel. Oh, the size of the screen, 2.5 inches across, or diagonal probably. Oh, best-selling game was Tetris. No kidding. And then Pokemon. Tetris sold more than Pokemon. All right. And then units shipped worldwide, 118 million. I don't think anything even comes remotely close to this. But I don't know. I haven't really researched that. So the speed. So the processor we're going to be emulating is 4.1 megahertz. It's a custom Sharp LR35902, which is a mix between a Z80 and I should say somewhere here. Similar to a Z80. Doesn't say that one, that's fine. So it's got 8 kilobytes of RAM. Can be extended to 32, I guess, if you put in a cartridge that has it, I'm not really sure. And 8 kilobytes of video RAM. So very, very limited memory for these. The Game Boy cartridges can support anywhere from 32 kilobytes to 1 megabyte. And it took 4 AAAs. We're obviously not going to be doing any power emulation. I just want to do a emulation that's good enough to play games. I'm not going to do an emulation that will simulate any hardware or anything. It's not going to be a simulation, it'll be an interpreter. So I had a link port. That is what that was. It was 13 ounces. Wow, that's pretty heavy, actually. Yeah, I got pretty lightweight after that. I think my smartphone was less than that. Dimensions, kind of an odd dimension. I don't think anything was ever this deep after this. Yeah, they got thinner and thinner. We don't need these details. Oh wow, I did not know there was no region lock on it. List of games, don't care. Backwards compatibility. That was the first system, so there's nothing to be backwards compatible with. Okay. So let's go over to the document. Let's look at the table of contents. So this is the Game Boy manual, CPU manual. This is provided to us by these generous people. Pan of Anthrax, Gaby, Merritt, Fizulin, Pascal Felber, Paul Robson, Martin Korth, Koopa, and Bowser. And the purpose of this is assembling language commands, timings, and opcodes, and everything you always want to know with the Game Boy, but were afraid to ask. Which Game Boy is this? This looks weird. Might be a color, but I don't see it there. So obviously this is a time before, well not really before, but 1989, 1999. I don't know, that's not this is from. This is from later than this. Maybe it's from 1999. But I'm obviously not going to print this document out. I can just read a PDF on my computer, it's fine. Let's make it a little bit bigger. Okay. So the table of contents. There's a forward, I think. Okay. And actually, be right back. Maybe you'll get some water. I just realized I'm going to do a bit more talking than I expected. myself some water. Stay hydrated, folks. So this document starts off with a foreword, some probably a letter from the authors. I'd like to read it. I'm going to open the window too to get some more light in here. And Cat will also enjoy some extra light. The sun is just in a spot now where it won't shine in my eyes. That's nice. Oh, this is some nice ambient lighting. It's cloudy out in Denver, which is very rare. Just cloudiness just brings that diffuse light, which is always really nice. Oh yeah. So the foreword is 1 page long. And then we go to the hardware specifications. So here's probably the rest of it. Oh, no, it's not. So here they're going to describe the hardware that was inside the Game Boy to us. So we're not going to do any hardware emulation, really. Like I'm not going to be doing any voltages or VHDL or whatever. We're just going to be doing interpretations. Whatever it takes to get the program to run on our computer. But we're going to read this regardless because the more you know, the better assumptions we can make. So there's another forward. They spelled it, I think, wrong. It should be spelled like this. And then they're going to put out a glossary for us. They're going to tell us the specs of the Game Boy. They're going to tell us about the processor. They're going to tell us the memory map. This is actually going to be really important for us. There's a general memory map, echo, user I/O, and reserved memory locations. We'll probably screenshot this and just refer back to it all the time during development. Cartridge types, special modi. I'm assuming that's Latin for mode. Okay, so yeah, there's a power-up sequence, stop mode, and a low power mode. This one we do care about. So when the Game Boy turns on, there's a BIOS that runs up, and that's what the Game Boy logo is coming down the screen. I need a video of that. Game Boy boot up, maybe. Game Boy boot logo. I don't want a color one. Don't want an advanced one. Okay, here we go. So it's just this. So there's no cartridge in here, I'm assuming. Oh, okay. What is this nonsense? There's a Raspberry Pi in there. I'll watch it. Because I'm assuming it's still going to come up with a logo. Here we go. So this is the logo. That power-up sequence there, I would like to see it on a real Game Boy. And it's got a bling. Okay, I'm going to go a little bit louder just in case. So that boot up sequence, that's built into the Game Boy in a ROM. And there's a very special thing around it that we'll talk about. That's also something that is, it's questionable the legality of it. I will be including the BIOS in the emulator though, the BIOS code for it. But that is a questionable legality thing. Okay, moving on from that. Oh, the power-up sequence is important though, because that program runs that little BIOS, like the Game Boy logo that comes down, and there's a bunch of registers and stuff that are set from that is assumed going into every game that is how it was, the end of that program, how those registers were set. So you can get around it. The way you can do that is how the registers are set after the boot sequence is known. So you just start off your emulator at those registers. I, however, would like to have the Game Boy logo scroll down, and then it'll just set the registers for me how it's supposed to. So that's just how I'm choosing to do it. It's also the first ROM that we're going to try to get up and running. Let's see. Stop mode, power mode, video. So here's how the video works, like how are the graphics shown on the screen. So there are tiles, there are sprites, and apparently there's a Sprite Ram Bug it talks about. I hope it talks about that you can have like up to 10 sprites per line and things like that. palettes. It doesn't seem to talk about in tiles, sprites it might, but there's color palettes you can choose between. Where they're stored is important. That's in the OAM. Okay. So then there's sound. That'll be probably the last part of my emulator. There's a timer. So it's just something that keeps track of how long the game has been running and stuff like that. There's serial I/O. There's interrupts. There's special registers. Okay, so that's under the hardware specifications. So then there's a Gameboy command overview. So this is where we're going to start most likely. We're just going to be going through this and implementing all of these commands. We could go through the ROMs and when one shows up that we don't have, then implement it. Or we can do them all in one, or not in one sitting most likely, but just do them all. I'm tempted not to do that. Because I feel like going through actual code would help me understand a little bit more how it works, even though this has a pretty good description of them. And if not, I'll be looking at other resources to figure it out. Super Game Boy, I believe that's the Game Boy Color. We're going to skip over this for now. And there's appendix, so emulator notes, typical timing diagram. So we might go straight to these after the forward, and then go to the hardware, and then the command. All right, so it's 3:40 my time. Let's go down to the forward. All right, this document was designed to help you programming the Game Boy Classic, Game Boy Pocket, Super Game Boy, and Game Boy Color. The basics. You will need additional documents for Game Boy Color, specific programming. All good thing we're not doing Game Boy programming. It was meant to be a complete handbook to start right off coding for the hardware. The document consists of 3 major parts. The first is the gbspec.txt, also known as the PAN document, by Pan of Anthrax, Merit Fayzulin. These people that are out earlier. This will be found in paragraph 1. The second is a mixture of several documents from Game Boy Assembly Language Primer, GALP, version 1 by Gabby. It contains opcodes, time duration, and the affected flags per assembly command. And this can be found in paragraph 2. The third is a summary of the specifications and commands for Nintendo Super Game Boy, so I'm not doing that. I don't think they meant paragraph. I really think they meant like chapters or sections. Because these paragraphs are going to be tens or hundreds of pages long. I think just tens. This document's too terribly long, 139. Information on how to get your emulator approved programs run on the real Game Boy can be found in the appendix. So, right, thanks to you. Also, timing diagram of the typical read and write operations of the classic Game Boy bus can be found here. So this is what it's saying is, if you want to write like a homebrew, like demo or game for the Game Boy, you can write your game for an emulator first before you run it on the actual Game Boy. So how to get your emulator approved for programs run on real Game Boy can be found here. So how do you prove that if it runs in the emulator, it'll run the Game Boy? That's what this is going to talk about. On the last page, quick reference that assembly commands included. Have fun. Ooh, that's really good to know. So I'm actually going to go down. So we're on page 5 right now. I want to check out that reference. Oh, wow, this is nice. Oh, I can screenshot this. Just for these page numbers really easily. What else is down here? Timing diagram. So I imagine I don't need to worry about this now. This is weird. Why would it scroll so slow? Okay. What other emulator notes do you have? Notes for getting assembly language programs to run on the emulator to run on the real Game Boy. This is from 1998. Right after the New Year. It's like really near now. Emulators tend to set all of the RAM to 0 on power up. Real Game Boys do not initialize RAM on power up. RAM is filled with random values on power up. You must clear it yourself if you wish it to be set to some known value. That's fair enough. So when you turn on a computer or any sort of machine that has RAM, it's not guaranteed what those bits are going to be before you initialize them. Like, it's going to be essentially random. I don't know if random is the right definition of it, but to our eyes and to our knowledge of what's supposed to be there, it's random. So it's not going to be all zeros, it's not going to be all ones. You know, obviously it could be, but it's probably not going to be. So the Game Boy is no different. When you turn it on, it's not going to spend the time clearing out the RAM. I don't know how long that would take on the Game Boy. I imagine that would take quite a while. It would be a noticeably larger startup time. You're just going to assume that if you're going to read from a location memory, you wrote something to it. If you didn't write something to it, oh gosh, what's that called? It's not a memory leak. Seg fault? It's not really a seg fault. You're just reading from somewhere. It's like when you have a pointer to memory, but you didn't initialize it, so you get garbage data back. I don't know why I'm blanking out on that. The real hardware could care less about the ROM checksum. 14E, 14F. The complement check, 14D, must be correct, or programs will lock up after scrolling the Nintendo logo. So, what this is saying, well, let's keep going. Use RGB fix-V in the development system to set the checksum in the complement byte after each source code compile. It doesn't matter whether you program in C or assembly, this program will fix it. So, in your ROM, if you're making a game for the Game Boy, there's a certain location in your ROM, I guess 14E and 14F, and 14D maybe, where you have to put the Game Boy logo. So it's just a bunch of bytes. I guess the assumption when they did this was no one was supposed to know it was the Game Boy logo. It was just a bunch of random bytes. This is such bad piracy protection, but the assumption was that if you were a pirate, you wouldn't know to put those bytes there, and then the program won't get past the Game Boy logo. When it scrolls down and goes pling, it'll just go pling, and then the Game Boy won't go past it. In fact, if you don't have the Game Boy logo, I don't even think you see the Game Boy logo. I think you just see whatever was there, just gibberish, and that just sits there, does nothing. So the BIOS, that thing that scrolls down and goes pling, will check your ROM, your Game Boy cartridge, to make sure that you have the Game Boy logo in there exactly correct. And then, only then will it let you continue. So that's what this is talking about. Or that's what this is talking about. I mean, it's just saying it again, I guess. When the LCD display is off, bit 7, so these are special registers, you can write to video memory at any time without restrictions. While it is on you, while it is on, you can only write to video memory during H blank and V blank. Code similar to this will work. Okay, so we'll get to this later when we get into the nitty-gritty. There should not be many instructions between the JR and Z, and write to memory load. Worst case of 64 CPU cycles, clock cycles are available to access main video memory, not OAM, following the JR and Z commands. The DI and EI commands above are only required if you're using serial timer or H or high to low interrupts. The LCD display is on at reset. Okay, so when you turn on the Game Boy, the LCD is on. So bit 7 is set to high, to 1, okay. Bit 7 of FF40, set to bit 7 of FF40. Okay, so I think that was a typo. I just meant this. Or else I'm just not understanding it. Before the LCD display can be turned off, you must wait for V-blank. One popular way of doing this is the following. Okay. So I'm not writing Game Boy code, so I don't really care. No, you should disable interrupts if they are enabled before executing the above code, or else the test of FF44 could prove invalid. Turning the LCD display on can be done at any time. If you're using sprites, then you should not use the following commands when their registered contents are in the range of FE00FEFF. Huh. If you don't follow this rule, sprite trash in the form of sprite blank will randomly affect your sprites. Interesting. Not important to me, but that is interesting. You know, I wouldn't have expected that. I don't really understand that. Normally, you should only make changes to Sprite Ram during VBlank unless you're an expert and know exactly what you're doing. Of course. The common way to do this is to use the GB DMA register to do a fast copy from your sprite table in RAM. To here. Okay. You need a sprite table in RAM with a starting address of XX00 with a length of 160. Many often use C through that for this purpose, but anywhere in RAM starting with is fine. You need to create a VBlank interrupt routine that contains the DMA command, followed by a short delay to allow the DMA to complete, and copy this routine to high RAM. The DMA command will not work in ROM or low RAM because these are disabled during DMA. After copying this routine to high RAM, you then need to enable the VBlank interrupt and then enable interrupts. Okay. So most of those are not going to be all that useful. Okay, so let's go down to here. So hardware specifications. So that was the forward. So hardware specifications, therefore. The following was typed up for informational purposes regarding the inner workings of the handheld game machine known as the Game Boy. Manufactured and designed by Nintendo Corporation Company Ltd. This info is presented to inform a user on how their Game Boy works and what makes it tick. Game Boy is copyrighted by Nintendo. Okay, we already remember that. I guess we didn't, but whatever. Any reference to a copyright material is not presented for monetary gain, but for educational purposes and higher learning. I will specify that this video series is also about educational purposes and higher learning. I'm not intending to make money off of this Game Boy. Terms. Game Boy, it's the original Game Boy. Game Boy Classic. GBP, the Game Boy Pocket, Game Boy Light. GBC, Game Boy Color, SGB, Super Game Boy. You know, I actually have no idea what the Super Game Boy even is. Oh, it's that thing they plugged into your Super Nintendo to play Game Boy games. Cool. So Game Boy specs. So it's an 8-bit CPU, similar to a Z80, which is a very simple microcontroller. It has 8 kilobytes of main RAM, 8 kilobytes of video RAM, 2.6 inch screen. So we already went over kind of a lot of. Oh, here's the number of sprites you're allowed to have on screen at a time: 40. However, you can only have 10 per line. So of these 140 lines, on one of them you can only have 10 sprites drawn to it. And of the whole thing, you can only have 40 total. Sprite size can be 8 by 16. That's a 2-tile clump. The minimum is 8 by 8. That is 1 tile. I guess tile is a little bit different than sprites, so I shouldn't be using that word. So clock speed, it is 4.2 megahertz roughly. So the Game Boy Color can run in double speed. So that's 8.3 here. So horizontal sync, this is how fast the screen can display. So it's not really relevant because it's a dot matrix, it's not a CRT. I don't know what I'm doing. Okay. So it can refresh, at these things that I don't think we actually care about. I might be wrong, but because it's a dot matrix. Oh, it is stereo. Okay, interesting. So it supports up to 4 channels with stereo sound, and we might look at it a bit later, but the 4 channels are special. You can have there's one that can do wave samples of different pitches, and the other 3, or then there's one noise generator, and the other 2 I believe are selectable between triangle and sine and stuff like that, and square, and pitch, and amplitude, all the good stuff. So here's the power text. I don't really don't care. So Nintendo documents describe the CPU instruction speed in machine cycles, while this document describes them in clock cycles. Here's the translation. Okay. So machine cycles. So this is how many, opcodes or instructions it can do. It can do 1 megahertz or 1.05 or 1 cycle. However, in clock cycles, it can do 4 or 4 cycles. So they're talking about machine cycles, I guess. So it can do 1 cycle per hertz. Or, sorry, I don't know. Ignore that. It can do 1,000, or what is this, 1 million? So that'd be 1 million or 100,000 or something. Do 1 million or 100,000 cycles per second. So the NOP instruction takes 1 cycle or no op. however long your clock cycles is for. So there are reasons for this. It could be for the I/O or for the video to do its own stuff in the background. It works on a different clock, and this is the common denominator. Okay, so let's dive in. The Game Boy uses a computer chip similar to an Intel 8080. It contains all the instructions of an 8080 except there are no exchange instructions. In many ways, the processor is more similar to the Zilog Z80. Compared to the Z80, some instructions have been added and some have been taken away. The following are added instructions, so I really don't care about the difference between the processors. If you are, here's a page that would be good for you. Okay, so here's the memory map. So this is going to be very, very useful for us. For now, we're just going to glance over it, but we're referring back to this a lot. Oh, it's interesting. I usually see it up the other direction, where zero's on the top and FF is at the bottom. They're looking at the other direction. So the top register, FFFF, are your interrupt enable registers. And then FF80 through FFF is your internal RAM. This range is your empty but unusable for I/O. So like this is a place you're not supposed to touch, I think. This range is your I/O ports. So that's how you know about like your button presses, I believe, and stuff like that. Don't use these either. So this is your OAM. So it's your object attribute memory, something like that. Oh, Sprite object attribute memory. So this is where you store all your sprites and tiles, like all of your descriptions of how your graphics should look. They live in here. You have an echo of an 8 kilobyte internal RAM. So this is an echo of this. It's literally the same. I believe there's some reason for it, like this is faster reading or something. Might not matter. You have a switchable RAM bank. So this can be various different things. So A through C, depending on which attributes are set, can change. Your video RAM. Another switchable ROM bank. And another switchable ROM bank. And then your BIOS also lives here from 0 to 100. And so when your Game Boy turns on, 0 through 100 is linked to your BIOS ROM. But then the second your PC gets to 100, then it resets and then it goes to your cartridge ROM. It no longer goes to your BIOS ROM. Okay. So here's your 32-bit cartridge. So when you plug in your Game Boy cartridge, it gets mapped to these spots. And then this one is switchable. Oh, here it's going to talk about the echo. The addresses E through FE or whatever, I'm not saying the zeros like I should be, appear to access the internal RAM the same as this. If you write a byte to address E000, it will appear at C000 and E000, similarly writing to a byte. So basically it's saying that they're identical. User I/O. There are no empty spaces in memory map for implementing input ports except the switchable RAM bank area. Talking about this. Not an option on the Super Smart card since its RAM bank is always enabled. An output-only port may be implemented anywhere between A000 through FDFF. So that's kind of up through here. Oops. Where was I? If implemented in a RAM area, care should be taken to use an area of RAM not useful for anything else. FE00 and above can't be used because the CPU doesn't generate an external WR for these locations. What is that? Is that a right? I don't know what they're saying. Let's see, what was I talking about? FE00 and above can't be used. It's these unusable areas. Oh. Okay. If you have a cart with an NBCI, 1, a ROM 4 megabits or smaller, and a RAM 8 kilobytes or smaller, or no RAM, then you can use pins 6 and 7. So this is talking about Game Boy game or program making. Then you can use pins 6 or 7 of the MBCI1 for 2 digital output pins for whatever purposes you wish. To use them, you must first put the MBC1 into 4 megabit ROM, 32 kilobyte RAM mode by writing 01 to 6000. So 6000 is in this area. The 2 least significant bits you write to 4000 will then output to these pins. 4000 is in this area. So actually, 4000 is the top of this area. I guess that's used to switch these out. Not really sure right now. So reserved memory locations. So these are the ones that are special. So once again, I'm not a Game Boy programmer. I'm just going to make an emulator, so these are less important for me. As long as I implement, well, I guess they are kind of important to me. But anyways, so 0. So these are your interrupts, I believe. So if you call RST with a 0, it'll call this address. If you call RST8, it calls this one, blah, 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 so on. These are interrupts. Your V blank is this one. Lcdc, or Lcdc Status interrupt. Time interrupt. So these are all very, very low memory addresses. So these are the very, very first bits of your ROM or your program. Serial transfer, high to low, P10 through P15. Okay. Internal information area is located from 100 to 14F. It contains the following values. So this is they actually give it to you here. This is the Nintendo graphic that's required to run on Game Boy hardware. If you change this, it won't run, it's saying, because the BIOS literally checks to make sure that these are all what they're supposed to be. This is the begin code execution point in a cart. So the BIOS runs from 0 to 100, and then 100 is when your program starts. So that's what this is saying. Usually there is a no-op and a JP instruction here, but not always. This is a jump. It's kind of like an if statement. Title of the game in uppercase ASCII. So here you put some metadata about your Game Boy, or about your program. If it is less than 16 characters, then the remaining bytes are filled with zeros. So I don't know entirely what the point of this is. I feel like it could be used for like, it's metadata. It's the title of your Game Boy, but like your Game Boy never shows that to you. All right, so 143. So color Game Boy, 0 or other, not color Game Boy. So there's more metadata stuff. High nibble of licensee code. Don't know about that one. Low nibble of licensee code. These are normally 0, 014B. We'll get down there. So Game Boy, Super Game Boy indicator. Cartridge type. So the Game Boy program can specify a whole bunch of different types of cartridges. Oops. I keep clicking shit. I don't know why I'm clicking that. So there's a bunch of different cartridge types. What is this button? What does this do? Highlight. For how many like ROM banks you have or memory banks. Apparently which features it needs to support, like Rumble. I don't know what. Does Game Boy have a Rumble? I mean, it must have. Just all this stuff that seems irrelevant to me right now. So how big is your ROM? How big is your RAM? Or how many banks is it, I guess? Is it meant for Japanese or not? Licensee code. So this is that 14B he was talking about. This is interesting. They had like specific game makers in here. Okay, so 14C, mask ROM version number. Complement check. Program won't run on Game Boy if not correct. It will run on Super Game Boy, however, if incorrect. So I don't know what the correct way is. I really don't need to know, though. Whoever is making the programs needs to know. So like if I run Tetris or something, these should be set correctly. Checksum. Produced by adding all bytes of the cartridge except for 2 checksum bytes and taking 2 lower bytes of the result. Game Boy ignores this value, so there's a checksum value, I guess, that they could have used for piracy detection or hacking, I guess, but they didn't. Or Game Boy, at least did. Cartridge type. So there was a cartridge types thing here, and now I'm just going to talk about that a little bit more. The following define the byte at cart location 147. ROM only. This is a 32 kilobyte ROM and occupies these parts of the memory map. So go back to the memory map. It was this to this. So 7 FFF is one below this. So scroll back down. See 7 FFF. Memory bank controller 1. Memory bank controller 1 has 2 different maximum memory modes. It can have a 16-bit ROM with an 8 kilobyte RAM, or a 4 megabit ROM with a 32 kilobyte RAM. It just means that you're kind of switching between which one do you need, a larger ROM, a smaller RAM, or a smaller ROM and a bigger RAM. So when you're switching between your ROMs, you get to keep your RAM, I believe. For here, it's the same, but when you switch between your ROMs, you switch more data, and you have less RAM to work with. A lot less, actually, which is kind of surprising. That there weren't more modes supported. Well, actually, we'll see. Memory bank controller 1 defaults to 16 megabit, 8 kilobyte RAM mode on power up. Writing a value minus X. Don't care. S equals memory model select. I'm very confused about this parenthetical thing. Writing a value into 6000 through 7FFF area will select the memory model to use. S equals 0, select 16.8, so that's this. S equals 1, selects 432. Writing a value into 2000 through 3FF, however, will select an appropriate ROM bank at 4000 through 7FFF. Values of 0 and 1 do the same thing and point to ROM bank 1. ROM bank 0 is not accessible from 4000 through 7FFF and can only be read from 0000 through 3FFF. So this to this. Okay, so that's just the reverse, where it's a larger RAM. So you can't write 2 ROMs. It's a read-only number. You can only write 2 RAMs. ROMs are very fast to read, usually. RAMs, are fast, but compared to a ROM, I believe they're not as fast. If memory model is set to 432, that's the other one that I'm trying to find and point to. Here, 432. 4 megabytes of RAM and 32 kilobytes of 4 megabytes of ROM and 32 kilobytes of RAM. Oh, I was wrong. Or no. This is a smaller ROM, yes. And this is a smaller RAM, okay. So, if it's set to 16.8 mode, which is still this one, writing a value into 4000 through 5FFF area will set the 2 most significant ROM address lines. The Super Smart card doesn't require this operation because this RAM bank is always enabled. Include the operation anyway to allow your code to work with both. Okay. Memory bank controller 2. So let me go up to that. So that was for cartridge types that are using Memory Bank Controller 1. There are ones that also have Memory Bank Controller 2. So these two here. And there's also Memory Bank Controller 3, 5, so 4. It's fine. So Memory Bank Controller 2. This Memory Controller works much like Memory Bank Controller 1, with the following exceptions. Memory Bank Controller 2 will work with ROM sizes up to 2 megabits. Writing a value into 2000 through 3FFF area will select an appropriate ROM bank at 4000 through 7FFF. RAM switching is not provided, unlike Memory Bank Controller 1, which uses external RAM. Memory Bank Controller 2 has 512 by 4 bits of RAM, which is in the controller itself. Still requires an external battery to save during power off, though. The least significant bit of the upper address byte might be 0 to enable or disable cart RAM. For example, the following addresses can be used to enable or disable cart RAM: 0 through 0FF, 200 through 2FF, 400 through 4FF, blah, 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 blah. The suggested address range to use for MBC2 RAM. I feel like that was left off. The least significant bit of the upper address byte must be one to select a ROM bank. For example, the following addresses can be used to select a ROM bank. Blah, blah. Memory Bank Controller 3. This controller is similar to MDC1, except it addresses all 16 megabits of ROM without requiring any writes to this area. Writing a value into 2003 FF area will select an appropriate ROM bank at this. Also, this MBC has a built-in battery-backed real-time clock, not found in any other MBC. Some MBC3 cards do not support it, or Alien 2 non-color version, but some do, Harvest Moon, Japanese version. So this is for the Game Boy Color. This controller is the first MBC that is guaranteed to run Game Boy Color double speed mode. It appears the other MBCs run fine Game Boy Color double speed mode as well. Oh, so this one's on Game Boy also, I guess, but it just doesn't run double speed. It is similar to MBC3, but can address up to 64 megabits of ROM and up to 1 megabyte of RAM. Wow, that's a big game. With a small, well, no, that's actually a big RAM, right? Alright, we're gonna keep going. Rumble? No. The lower 8 bits on the 9-bit ROM bank select is written to 2000 through 2FF area, while the upper bit is written to the least significant bit of the 3000 area. Writing a value into 4000 through 5FF area will select an appropriate RAM bank at something if the cart contains RAM. RAM sizes are 64 kilobit, 256 kilobit, and 1 megabit. Also, this is the first MBC that allows ROM bank 0 to appear at the 4007 FFF range by writing 0 to the ROM bank select. Rumble cards. I'm going to skip over that. This controller made by Hudson Soft appears to be very... What is this? Yeah, I don't think I need to look at this. It looks to be very specific to something else. Special modes, power-up sequence. So the Game Boy is powered up with 256-byte program, which is 100 in hex. Starting at memory location 0 is executed. This program is located in a ROM inside the Game Boy. This is the BIOS I was talking about. The first thing the program does is read the cartridge locations from 104 to 133, that's the Game Boy logo, or Nintendo, and place the graphic of a Nintendo logo on the screen at the top. This image is then scrolled until it is in the middle of the screen. 2 musical notes are then played on the internal speaker. Again, the cartridge locations 104 and 133 are read, but this time they are compared with a table in the internal ROM. If any byte fails to compare, the Game Boy stops comparing bytes and simply halts all operations. Game Boy and Game Boy Pocket. Next, the Game Boy starts adding all of the bytes in the cartridge from 134 through 14D. A value of 25 decimals is added to this total. If the least significant byte of the result is not a 0, the Game Boy will stop doing anything. Wow. Super Game Boy. So even though the Game Boy and Game Boy Pocket check the memory locations, the Super Game Boy does not. If the above checks pass, then the internal ROM is disabled, and the cartridge program execution begins at location 100 with the following register values. So this is what it looks like after the BIOS has RAM. So if you don't want to include the BIOS, because it's kind of a gray, I don't know if it's gray really, but I think it's a gray area of if you're allowed to have that software or not. This is what it looks like when it's done running. So you can just plug these in and skip that. However, I really want that Game Boy logo to go down and go pling. It just won't feel right otherwise. So we're going to run the program, and then these will be set for us by that program. It is not a good idea to assume the above values will always exist. A later version of Game Boy could contain different values than these at reset. Always set these registers on reset rather than assume they are as above. Please note the Game Boy internal RAM on power up contains random data. All of the Game Boy emulators tend to set all RAM values to 0 on entry. Cart RAM the first time it is accessed on a real Game Boy contains random data. Really? It will only contain known data if the Game Boy code initializes it to some value. Oh, Cartridge RAM. Right. I was thinking Cartridge ROM. Stop mode. The stop command halts the Game Boy processor and screen until any button is pressed. The Game Boy and Game Boy Pocket screen goes white with a single dark horizontal line. The Game Boy Color seems to go black. So I'm not familiar with this. Low power mode. It is recommended that the halt instruction be used whenever possible to reduce power consumption and extend the life of the batteries. So this is really about writing Game Boy games. This command stops the system clock, reducing the power consumption of both the CPU and ROM. The CPU remains suspended until an interrupt occurs, at which point the interrupt is serviced and then the instruction immediately following the halt is executed. If interrupts are disabled, then halt doesn't suspend operation, but it does cause the program counter to stop counting for some instruction on the Game Boy. Depending on how much CPU time is required by a game, the halt instruction can extend battery life anywhere from 5 to 50%, or even more. So it's pretty much just a sleep, it sounds like. So if you know that you don't need all the cycles in this frame, then you can just halt, and then it'll pick up later, it sounds like. Warning, the instruction immediately following the halt instruction is skipped when interrupts are disabled. Okay. This skipping does not seem to occur on the Game Boy Color. Okay, so this is terribly important to us. This combination of a halt. Yeah, this is entirely important. Come on, Edge. I don't want all this dumb stuff. Just like turn that dumb stuff off. Oh, you have a dark theme? That's cool. Oh, that's why it's using Bank, because we're using Edge. It's so obvious now. Okay, so let's see if it's in here. So I can't turn off those features, it looks like. I can turn off this, because I don't use this browser. These things will forever live. Yeah, let's talk about the video. Tiles. That's interesting. This wasn't in the... I believe this wasn't in the table of contents. So wait, what page am I on? I'm on page 22. Yeah, oh, it was. It's right there. Interesting. The main Game Boy screen buffer consists of 200 by 256 pixels, or 32 by 33 tiles, 8 by 8 pixels each. So a tile is 8 by 8 pixels. Okay, here we go. Only 164 by 144 pixels can be displayed on the screen. That's why I was getting confused. I was getting confused by this. So it can draw a canvas, I guess, that's 256. So this is what you see on the screen. Registers scroll X and scroll Y held the coordinates in the background to be displayed in the left upper corner of the screen. Background wraps around the screen. When part of it goes off the screen, it appears on the opposite side. Interesting. An area of VRAM known as background tile map contains the numbers of tiles to be displayed. It is organized as 32 rows of 32 bytes each. Each byte contains a... It's weird that the margins change. Oh, it's like on the left side of the page or it's on the page. Right. Each byte contains a number of tiles to be displayed. Tile patterns are taken from the tile data table, located either 8000 through AFF or 8800 through 97. Let me look that up in the... It's on page 23. Look that up in the memory thing. Okay, so that's in... Oh, it's in here. Yeah, I wasn't expecting that. All right. In the first case, patterns are numbered with unsigned numbers from 0 through 255, i.e. pattern 0 lies at address 8000. In the second case, patterns have signed numbers, negative 128 through 127. Pattern number 0 lies at address 9000. The tile data table address for the background can be selected via LCDC register. I'm assuming that's the LCD controller. Besides background, there's also a window overlaying the background. Oh, so I think it's called like the awesome Game Boy talk. Okay, so we're going to do gbdev awesome. Oh, Ultimate. That's what it was. So there is a video, the Ultimate Game Boy talk. And this video, oh, this is on YouTube. Okay. So this video talks about all sorts of stuff, including, you know, this is really sucky compared to YouTube. Okay. But I chose to link to that one, I guess. I know it's on YouTube, though. But it talks about all this. It talks about the OEM. It talks about, what was I just reading about? Oh, the window. The window is really interesting in the Game Boy. So the window is intended to be used for UI. Let's see if we can find out where he's talking about that. So here, these are the tiles, the green spots. And these are sprites. So sprites can be placed anywhere. Tiles can be placed in this grid. And you have a scroll X and scroll Y to move the background around. So per line, you can only have 10 sprites. So he's showing this line here has 11, so it doesn't draw that. And then the next one too. Okay, so here's a window. This right here is a window. It doesn't, I believe it doesn't react to scroll X and scroll Y. It's just like a fixed part of the screen. He's showing off some demos. Oops. Oh yeah, the window is not scrollable. It is always displayed starting from the left to upper corner. The location of the window on the screen can be adjusted via these special registers: window position X and window position Y. Screen coordinates of the top left corner of a window are window position X minus 7 and window position Y. The tile numbers for the window are stored in the tile data table. None of the Windows tiles are ever transparent. So you can't have a transparent pixel in your window. Both the background and window share the same tile data table. Both background and window can be disabled or enabled separately via bits in the LCD controller register. If the window is used and scanline interrupt disables it, either by writing to this or setting it greater than 166, and the scanline interrupt a little later on enables it, then the window will resume appearing on the screen at the exact position of the window where it left off earlier. This way, even if there are only 16 lines of useful graphics in the window, you could display the first 8 lines at the top of the screen and the next 8 lines at the bottom if you wanted to do so. WX may be changed during a scanline interrupt to either cause a graphic distortion effect or to disable the window, but changes to the WI are not dynamic and won't be noticed until the next screen redraw. Interesting. So you can, I think this means that you can split your window into the left and right. You can't split it in the top and bottom, like both left and right and then both top bottom. The tile images are stored in the tile pattern tables. Each 8x8 image occupies 16 bytes, where each 2 bytes represent a line. So here's a line, 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 and here's a line. This is a really weird way to look at it. As it was said before, there are 2 tile pattern tables at 8000 through 8FFF. And at this, the first one can be used for sprites, the background, and the window display. Its tiles are numbered from 0 to 255. The second table can be used for the background and the window display, and its tiles are numbered from -128 to 127. It's really weird that they did unsigned and they did signed. Game Boy Video Controller can display up to 40 sprites, either in 8x8 or 8x16 pixels. So you can have 2 tiles together, or sprites. We're moving on to the section sprites. So you can have a single sprite that's 8x8, or 2 sprites together, which is 8x16. It's just 2 sprites next to each other. Because of the limitation of hardware, only 10 sprites can be displayed per scan line. Sprite patterns have the same format as tiles, but they are taken from the sprite pattern table located here, and have unsigned numbering. Sprite attributes reside in the sprite attribute table, OAM, object attribute memory, at here. OAM is divided into 40 4-byte blocks each, which correspond to a sprite. In 8x16 sprite mode, the least significant bit of the sprite pattern number is ignored and treated as 0. Alright, when sprites with different x-coordinate values overlap, the one with the smaller x-coordinate closer to the left will have priority and appear above any others. When sprites with the same x-coordinate values overlap, they have priority according to the table ordering. So, where they are in the table. Yeah, so the lower the number, the higher priority they get if they have the same x-coordinate. Otherwise, it's where they're on the x line, so things further left appear on top. Please note that sprite x0y0 hides a sprite. To display a sprite, use the following formulas. What? Sprite screen position x. Oh, I see. So this is off the screen a little bit. Upper left corner of the sprite is sprite x minus 8. Upper left corner of the sprite, sprite y minus 16. To display a sprite in the upper left corner of the screen, set x to 8 and y to 16. Only 10 sprites can be displayed on any one line. When this limit is exceeded, the lower priority sprites won't be displayed. To keep unused sprites from affecting on-screen sprites, the y coordinate to y equals 0 or y 144 plus 16. Just setting the x coordinate to x equals 0 that on a sprite will hide it, but it will still affect other sprites sharing the same lines. Interesting. Blocks have the following format. Byte 0, the y position on the screen. Byte 1, x position on the screen. Byte 2, pattern number. So some tile numbers are signed, some are unsigned. LSB, least significant bit, is ignored, treated as 0, in 8x16 mode. Bit 7 priority. If this bit is set to 0, sprite is displayed on top of background and window. If this bit is set to 1, the sprite will be hidden behind colors, 1, 2, and 3 of background and window. Sprite only prevails over color 0 of background and window. Bit 6, Y flip. Sprite pattern is flipped vertically if this bit is set to 1. Oh, this is cool. Bit 5 XFlip. Okay. So for each spine in the screen or tile, we have 4 bytes. Yeah, we have 4 bytes. So 1 byte is used in the Y position, 1 byte's used in the X position, 1 byte's used for which sprite or tile we're drawing. And we have a bunch of bits we're going to use now. So the priority of it, if it's upside down, if it's mirrored left and right, and then which palette should it use? Sprite colors are taken from object 1 palette. If this bit is set to 1, it is taken from object 0 palette. Oh, sorry. If it's set to 1, you take it from object 1, otherwise it's object 0. There's only one otherwise for bits. So Sprite Ram Bug, let's see what this is talking about. There is a flaw in the Game Boy hardware that causes trash to be written to OEM RAM if the following commands are used while their 16-bit content is in the range of this. Okay, so I don't think we have to worry about this. Only sprites 1 and 2 are not affected by these instructions. Interesting. Sound. So I'm going to see how long sound is real quick. And then I might stop reading out CPU instructions because it's been a lot of reading. There's a timer too. Okay, so it's actually going to be a little bit. Let's go through sound. I do like sound. There are 2 sound channels connected to the output terminals. Sound output 1, sound output 2, I guess for stereo. There is also an input terminal, voltage in, connected to the cartridge. It can be routed to either of both output terminals. Game Boy circuitry allows producing sound in 4 different ways. Quadrangular wave patterns with sweep and envelope functions. Quadrangular wave patterns with envelope functions. Oh, these are the 4 types. So you can have a wave pattern with a sweep and envelope. You can have a wave pattern with an envelope. You have a voluntary wave pattern from wave RAM, or white noise with an envelope. Okay. These 4 sounds can be controlled independently and then mixed separately for each of the output terminals. So this is the sample one I mentioned. This is the noise one I mentioned, and these are like the signs and squares and triangles. And then I didn't know. So you have a choice with a sweep and without a sweep. And they have envelopes like a tag and stuff like that. These 4 sounds, okay. Sound registers may be set at all times while producing sound. That's cool. So you can just dynamically change what it sounds like. When setting the initial value of the envelope and restarting the length counter, set the initial flag to 1 and initialize the data. Okay, so your envelope has like a duration, so I guess this is how you do it. You set the initial flag to 1. Under the following situations, the sound on flag is reset and the sound output stops. When the sound output is stopped by the length counter, an overflow occurs at the addition mode while sweep is operating at sound 1. So I believe a sweep is like when you change the pitch of something. So it can go like woo, like that would be a sweep. You can also do it with frequencies. So I don't know what they have in mind for sweep, but my impression of a sweep is when you, I think it's when you do a linear like interpolation over one of the sound parameters. We'll see what they mean. When the overflow occurs, the addition mode will sweep. So maybe if you don't want this feature, you wouldn't use sweep, and that's why they have the second version here without sweep. When the sound off flag for sound 3, bit 7 of NR30, is at 0, the cancellation of the off mode must be done by setting the sound off flag to 1. By initializing sound 3, it starts its function. A little bit confused by this, but it's okay. When the all sound off flag, there's another manual that we can pull up for sound when we're ready for it. When the all sound off flag, the 7 of NR52, is set to 0, the mode registers for sounds 1, 2, 3, and 4, you have 4 voices, are reset, and the sound output stops. Note, the setting of each sound mode register must be done after the all sounds off mode is canceled. During the all sound off mode, each sound mode register cannot be set. Okay. During the all sound off, Game Boy power consumption drops by 16%. While your programs aren't using sound, then set the all sound off flag to 0. It defaults to 1 on reset. Interesting. These tend to be the two most important equations in converting between Hertz and Game Boy frequency registers. Sounds will have a 2.4% higher frequency on Super Game Boy. Huh. It's interesting how different the Super Game Boy is when it's supposed to be like an emulator. So Game Boy frequency equals 2048 minus that. And our Hertz, which is what we hear, is that divided by that, which is pretty much an equation of that. Oh, nice, Game Boy. So it's just to plug the result of this into whatever. Sometimes it's useful to have a timer that, okay, so now we're talking about timers. Sometimes it's useful to have a timer that interrupts at regular intervals for routines that require periodic or precise updates. The timer in the Game Boy has a selectable frequency of 4K, 16K, 64K, or 256K, or Hertz. This frequency increments the timer counter, the TIMA. I'm assuming it's timer A, or maybe it could be time accumulation too. When it overflows, it generates an interrupt. It is then loaded with the contents of timer modulo, or TMA. The following are examples. This interval timer interrupts 4K times per second. Wow. That is quite the interrupt. Wow. This one interrupts 64,000 or 64K times per second. That is intense. So I'm going to skip over serial IO. I don't think this is important. This is talking about when you plug that wire between two Game Boys. I believe. So this would definitely be like a stretch feature. It'd be very hard to have two emulators that talk with this. You could technically do it through like two emulators on the web page, or you could do it with a like WebRTC type thing. It's definitely a stretch. So I'm going to assume that that's what this is talking about. Okay. Interrupts. Let me see how long interrupts is real quick. 32. Okay, so I'm going to go through interrupts, and then we're going to end at special registers, and that kind of starts the CPU stuff. So let's go through these. So interrupt procedure. The IME, the interrupt master enable flag, is reset by DI and prohibits all interrupts. So this is disable interrupts. It is set by the enable interrupt and acknowledges the interrupt setting by the IE register. Interrupt, I don't know, interrupt enable. When an interrupt is generated, the IF flag will be set, the interrupt flag. If the IME flag is set and the corresponding interrupt in the IE flag is set, the following three steps are performed. Reset the IME flag and prevent all interrupts. The program counter is pushed onto the stack. Jump to the starting address of the interrupt. Resetting of the interrupt flag register, which was the cause of the interrupt, is done by hardware. During the interrupt, pushing of registers to be used should be performed by the interrupt routine. Once the interrupt service is in progress, all the interrupts will be prohibited. However, if the IME flag and the IE flag are controlled, a number of interrupt services can be made possible by nesting. Wow. Return from an interrupt routine can be performed by either return interrupt or return instruction. The return interrupt instruction enables interrupts after doing a return operation. Okay. If return is used as a final instruction in interrupt routine, interrupts will remain disabled unless an EI was used in the interrupt routine or is used at a later time. The interrupt will be acknowledged during opcode fetch period of each instruction. Interrupt descriptions. The following interrupts only occur if they have been enabled by the interrupt enable registers at FFFFF. And the interrupts have actually been enabled using the EI instruction. VBlank. The VBlank interrupt occurs 60 times a second on a regular Game Boy and 61 times a second on a Super Game Boy. This interrupt occurs at the beginning of the VBlank period. During this period, video hardware is not using video RAM, so it may be freely accessed. This period lasts approximately 1.1 milliseconds. So they have a VBlank because it's kind of pulling over from the CRT age, but it used to be that, I watch my cursor, I guess, that your CRT or cathode ray tube, the old monitors that buzz that we don't use anymore, had curved screens that were affected by magnets. They would shoot electrons using a magnet, and they'd scan across, and they'd scan across, and it'd scan across, and they'd do that for every single pixel. It'd scan a row across, scan a row across. So this would be an H-blank. So I'm scanning a line across, then H-blank would happen. Nothing's happening here. I'm just moving to the left, and I'm scanning a line here, then H-blank would happen. Nothing's happening here. So there is no H-blank, right? Yeah. So they have a V-blank. It's kind of video blank, maybe I should be calling it, because there is no real V-blank here. But what happened was the cathode ray tube would go across, go across, go across, go across. So you could do some minimal amount of work doing this H-blank when the thing was moving back over, and then some work would be doing, and then you could do some work during this H-blank. This would be like Atari or something. And then it would get down to the bottom, and there'd be a V-blank. So it would go back up the screen, and that you'd have a lot more time to do some work. So with the Game Boy, we still have to push pixels to the screen, so it's going to pushes them all to the screen, I believe, just like all at once, maybe. And then the V-blank happen. It gives you some time to do a bunch of work before the next frame is rendered, and then you get some time to do some work, and the next frame is rendered. So that's what this is talking about. So V-blank interrupt happens periodically, and then you get some time to do some work, 1.1 milliseconds, which is a lot in microcontroller time, I guess. So if it's happening 16 frames a second, it means there's 16 milliseconds per frame. So you get 1 during the V-blank. So Lcdc status. There are various reasons for the interrupt to occur as described by the stat register. One very popular reason is to indicate to the user when the video hardware is about to redraw a given LCD line. This can be useful for dynamically controlling the screen X, screen Y registers to perform special video effects. So you can maybe like shake the screen, I'm assuming. Or you could even do some other things, like you can warp sprites maybe. Timer overflow. This interrupt occurs when the timer A or accumulator, I'm not really sure, changes from full to 0. So you just get to know like when it's been at full, when the timer is resetting. Serial transfer completion. This interrupt occurs when a serial transfer is completed on the Game Link part. So if you have a plug-in and you're plugged into another Game Boy. High to low, P10, P13. This interrupt occurs when I transfer any of the keypad input lines from high to low. Due to the fact that the keypad bounce is virtually always present, software should expect the interrupt to occur 1 or more times for every button press, and 1 or more times for every button press or release. So it talks about bounce has to be assigned to any button making or breaking a connection. During these periods, it is very common for a small amount of oscillation between high and low states to take place. So basically what it's saying is, let's look at a button diagram. There we go. No. Yeah, okay, so this one. So this is a button. So down here you have 2 lines coming in. So this could be like, it's basically, you have a button here. And then this yellow are things that are conductive to electricity, and these are 2 like electric lines. So maybe on this side you have a piece of hardware that's checking to see if you have a high voltage or a low voltage. And this is either a high voltage or a low voltage. So let's just say this is high, and this one's checking to see if it's high. So while these are not connected, this is low. So when you press down this button, you're going to drive this yellow thing down into here. And then you have a full connection through here. So this becomes high. But while you're doing that, there's like connections that intermittently get pressed and unpressed because it's just electricity, so it can like arc, and I don't really know what's going on. But when you press it, it might go up and down like 10 to 100 times, and what you think is a fluid press. Like you're just pressing it down, like you're just going boop, and it might turn on and off like 10 to 100 times or whatever in there. So what this is saying, this bounce it's doing, you need to debounce it. So when you're pressing it down, you need to look over like a 100 millisecond time window, or probably a 10 millisecond time window, or 1 millisecond. And you need to see, has it been pressed or has it been released in that time period, and then don't listen to other ups and downs during that. Just say like, it's been pressed, like that's it. Or you just press it once and then you ignore it for like 9 milliseconds and then you listen to it again. So there's an interrupt for when one of the buttons are pressed. So 10 through 13, that's 4 high to low, P10. So I don't really know what P10 through P13 is, but I feel like there should have been 8 of them. So that's interesting. So if there's 4, maybe if you're using the bits, probably using just bits. So on one byte, you can listen to all 8 of them if they go from 0 to 1, stuff like that. Okay, so I'm going to stop here at special registers. We'll continue another time. But it's basically when we start getting into, actually, let me look through these. When do we get to instructions? Actually, this is long, so we're going to keep it. So these are all the special registers. These are registers that the hardware is going to set for me, or I can set, and the hardware reads it and does special things like sound or power, or I don't know, just various things. Okay, so it goes on for quite a while. There's a lot of special registers. It does make sense, though, because we do need to talk to the hardware. Oh my gosh. Just keeps going. Okay, and then the CPU part starts. So I'm not going to go through these today. I don't have time. Tomorrow we'll go through, or another time, not necessarily tomorrow. Another time we'll go through the special registers, and then we'll start on the CPU instructions, and maybe we'll start even writing our emulator. We'll start rigging it up. But having a good background knowledge of what we're going to be doing before we start writing, I think is a really good idea. Some of this might be overkill. Like we'll definitely be referring back to it, even though we read it all. We'll be referring back to this over and over and over. That's just the nature of writing complex systems. Emulators are complex systems, and then, or the Game Boy is a complex system, and then writing a program on a different system that simulates or emulates the Game Boy system is a complex program itself. So it's not a read this once and remember everything. It's a read this once and then come back to it for little nibbles, maybe a million more times. So yeah, here are all the instructions. So I believe like the rest of the manual is actually instructions. Oh, yeah, we're still going through instructions. Okay, so there's where it stopped. Or no. I mean special commands. Yeah, but basically, it was like pages 40 through 120. That's for the CPU. So, thanks for tuning in. If you're interested in Game Boy emulator development, I'm going to be doing this in, I think, TypeScript. It's either going to be Rust or TypeScript. I'm really leaning towards TypeScript, but it could be Rust. I'm not really sure yet. Yes, I'll mention this. There are lots of TypeScript and Rust emulators out there for Game Boy. I haven't checked, but I just guarantee there are. Emulators are just fun to write. There's actually a really good blog post on this. It might be on this page. I'll see if it is. It's called like Why I Wrote. Why did I spend 1.5 months creating a Game Boy emulator? And he goes into a lot of detail on like, why did he do this? His family and friends are watching him, like, there's ones that already exist that are really good. It's like, yes, but like, the point of writing this isn't to play the games, even though the games are really fun. Like Game Boy had some really good games on it. It's the writing of it that's the fun part, and the implementing a whole other system that doesn't even run on modern hardware to effectively emulate and then interpret it and run it on modern hardware is the fun part. So this is a good blog post. Why did I spend 1.5 months creating a Game Boy emulator? If you want to know why we might do this, it's definitely not to create an emulator for people to use. Just a fun learning experience. Because they're very complex systems, no matter how you go about it. So, once again, this is Corvid Coder. I'll be signing off here. If you like this video, give it a thumbs up and subscribe. Yeah, thank you very much. I'll see you another time.